Today's lesson is on energy. We'll be discussing the different forms of energy, especially those that pertain to our coasters we will be making in this unit. So we define energy as the ability to cause change. So if an object has energy or possesses energy, it can cause a change in motion, a change in direction, a change in form. So energy is the ability to cause some kind of change. And in our case, we'll be talking about energy's ability to cause a change in motion. So there are several different forms of energy that we come across every day. So the main ones are electrical, chemical, radiant, and thermal energy. So electrical energy is used when making toast, for example. So you plug in your toaster, the toaster heats up. So the electrical energy is coming from a power plant or from the toaster. The second type of energy is chemical energy. So this is energy stored in bonds, in molecules. So when you digest food, you break bonds and reform some new bonds, and that change in energy is that energy that your body uses to function. So chemical energy is energy stored in food, or we could talk about chemical energy in gasoline or fuels. So again, we're breaking bonds, reforming bonds, and that difference in energy is energy released to do some kind of work. Radiant energy is a form of energy that comes from the sun, which is very similar to thermal energy. So thermal energy is energy in the form of heat. We'll be focusing on energy that is called mechanical energy, so energy associated with motion or position of an object. So kinetic energy, we've heard that word before. Kinetic, we've talked about it in terms of kinetic friction, so friction an object experiences when it's moving. So kinetic energy is the energy of a moving object. So it's the energy it possesses because of its motion. So kinetic energy depends on its mass of the object and the velocity. So the more massive your object is, the more kinetic energy it's going to have. The higher your velocity of your object, how fast it's moving, is also going to increase its kinetic energy. And so for energy, we have a new unit, which is called the joule. And so it's a capital J again because it's named after a scientist. And so it's the SI unit to measure energy. So all the forms of energy we're going to be talking about are going to be measured in joules, so capital J. Now we can calculate kinetic energy using this equation. So KE stands for kinetic energy, and that equals 1/2. So in your calculator, you could type it in as 0.5, times by m. M is your mass, times by your velocity squared. So we're only squaring the velocity. We're not squaring the m or the half. So it's 1/2 times m times your velocity squared. And so just by looking at this equation, velocity actually is going to affect our kinetic energy more than our mass because we're actually squaring our velocity. So let's try an example problem. So a jogger with a mass of 60 kilograms is moving at a speed of 3 meters per second. What is the jogger's kinetic energy? So first, we should always write out our variables that we're given. So we have mass, velocity, and kinetic energy in our equation. So by looking at our problem, kilograms is a unit of mass. We know our mass is 60 kilograms. Our velocity is going to have units of meters per second, so we know our velocity is 3 meters per second. That means we need to find our kinetic energy. So if we remember our equation, kinetic energy equals 1/2 mass times velocity squared. So I'm going to plug in my numbers. So instead of writing 1/2, what I'm going to do is write what I would plug in my calculator. So I'm going to plug in 0.5, and I'm going to times that by my mass, which is 60, times by 3 squared. So I'm only squaring the 3. So I'm going to plug that into my calculator to get an answer. 0.5 times 60 times 3, and I'm going to hit the squared button. So I get a kinetic energy of 270. And my unit for energy is joules. So I'm going to put a capital J. And so a good clue to know that we're talking about kinetic energy is that you have a velocity and your object is moving. So there are other forms of energy associated with an object's position or motion. So we call that potential energy. So potential energy is stored energy due to an object's position. So one form of it is elastic potential energy. So if we stretch a rubber band, now it's not moving yet, it's still stretched, but it has the potential to release that energy and decompress. Chemical potential energy also exists. So in our food and in our fuels, that has the potential of releasing energy if we break those bonds and then reform them. Gravitational potential energy is energy due to an object's position above the ground. So if we're standing on a bridge, we have the potential to release that energy and fall downwards. So elastic, let's just define that a little bit more. So elastic energy is energy stored by things that are stretched or compressed. So we can talk about stretching a rubber band, and it has potential of releasing it and it going back to its original position. But in that releasing it, we release some energy. Or we can talk about a spring being compressed. So if we compress it down to a smaller size, it has the potential of us releasing it and then it causing motion, which releases some energy. So two good examples of elastic potential energy are rubber bands and bungee jumping. The next form of potential energy is chemical potential energy. So this is energy stored between the chemical bonds in atoms. So if we go through a chemical reaction by burning some fuel, we break some of those bonds and we reform them. And the difference in that energy between breaking and forming is energy released in the form of motion, in most cases in our cars. But the one we're going to focus on is gravitational potential energy. So sometimes we shorten it to say GPE, but sometimes we also just put PE for potential energy. And so gravitational potential energy is energy stored in things above the Earth's surface. So our gravitational potential energy is going to depend on the mass of our object, the acceleration due to gravity on Earth, which remember we always know is 9.8, symbolized with the letter G, and the height above the ground. So the more massive your object is, the farther you are off the ground, the more potential energy your object is going to have. And we can calculate that by using this equation. So our gravitational potential energy, again remember sometimes we just write PE, potential energy, equals our M, which is mass, times G, which is 9.8, times H, which is the height. So mass times gravity times height. So let's try an example problem. So what is the gravitational potential energy of a ceiling fan that has a mass of 7 kilograms and is 4 meters above the ground? So again, we're going to write out our variables first. So our equation is our gravitational potential energy, which equals mass times gravity times height. So our values are potential energy, mass, gravity, and height. So our potential energy is what it asks for. So what is the gravitational potential energy? So that's our unknown. So I'm going to put a question mark. Our mass should be measured in kilograms. So we look for that number, or that unit, next to a number. So we have 7 kilograms for our mass. Gravity, we always know, is the acceleration due to gravity on Earth. So 9.8 meters per second squared. And our height is 4 meters above the ground. So all we need to do is plug in our numbers into our equation. So we don't know potential energy. But we have our mass, so 7, times gravity, which is 9.8, times our height, which is 4. So we're going to plug that into our calculator. 7 times 9.8 times 4. I'm going to get an answer of 274. And again, this is energy, so its units are joules. So a pretty simple calculation for potential energy. Just mass times gravity times height. So let's practice identifying the difference between our two forms of energy we just calculated. So is it potential or is it kinetic? So remember, potential is things above Earth's surface that are not moving. Kinetic energy is things associated with motion. So a football is kicked and leaves the foot with a speed of 30 meters per second. So is that potential or kinetic? And so we have a speed, so 30 meters. So we know that has to be kinetic energy. So number 1 should be kinetic. So a person is about to roll down a hill that is 21 meters high. So there's no motion on this one. It says it's about to roll down the hill, so we don't have motion. So we know it can't be kinetic energy. And we get the clue that it's 21 meters high. So it's above Earth's surface. So we know that has to be gravitational potential energy. So number 2 is potential energy. Number 3, a person stands on top of a platform diving board. So again, the person is just standing there, so there's no motion. So that eliminates kinetic energy. Kinetic energy have to have motion. But we're above Earth's surface, so that tells us that it will be gravitational potential energy. So number 3, potential energy. And then number 4, a car is traveling with a speed of 40 meters per second. So because we have a speed, that gives us the clue that it's going to be kinetic energy, energy associated with motion. So number 4 is kinetic energy. So how do these two relate to one another? So we have something called the law of conservation of energy, and it states that energy cannot be created or destroyed, it can only be transformed. So we can't lose energy in our in our universe. It has to go somewhere. So if I go down a roller coaster, so I get pulled to the top, so I'm increasing my potential energy. When I get to the top of the coaster, I have a maximum amount of potential energy. As I go down the other side of the coaster, my potential energy gets converted into kinetic energy. So I can't lose or gain energy. It can only be transferred into some other form of energy. So all the energy in our universe is only conserved. It's used over and over again. A lot of time we lose some of that energy to friction or heat or thermal energy, but it goes somewhere. It just gets converted into a different form. So for example, like a power plant burns coal, which is chemical potential energy, converts that into electrical energy sent through your house. Let's say it gets to your toaster. That toaster uses that electrical energy, converts it into thermal energy. And so the energy can't be created or destroyed. It just gets transformed into something new. So when we talk about moving objects, which we will be doing here in this unit, we want to talk about mechanical energy. So when we talk about the conservation of energy, mechanical energy is what's getting conserved. So we symbolize mechanical energy with the letters ME. So in motion, mechanical energy is conserved. So mechanical energy is just the sum of your kinetic plus your potential. So just like in that coaster example, the kinetic and potential energy increase or decrease depending on where you are. So as you go up the first hill of the coaster, you're increasing your potential energy. As you come down the other side, that potential energy gets converted into kinetic. But the total of those two added together will always be constant. Your mechanical energy will always be the same. So your kinetic plus your potential energy. So is it always conserved? So if we think about this example, so while coasting along a flat road on a bicycle, you know that you will eventually stop if you don't pedal. So how does this fit our law of conservation of energy? So if energy is conserved, why wouldn't your kinetic energy be constant? And so that is because friction and air resistance cause some of that energy that related to your motion, your kinetic energy, to be converted into thermal energy. And so the effect of friction in a lot of our cases is that energy is not created or destroyed. It's converted into thermal energy. So energy conservation. So in a roller coaster, which we'll be working with here in a couple of examples, a car can be lifted to some initial height. We give it potential energy. As it goes down the other side, it converts it into kinetic. So you're going to do a mock experiment a little bit later here today on how a roller coaster works. And then later on in this unit, we'll be building roller coasters. So we're going to be observing this law of conservation of energy and our kinetic and potential energy problems.